All right, this is Further Pure 2 from 2023. Let's just do it. The characteristic equation is just the determinant of A minus lambda I. So you take away lambda from the leading diagonals because when you times it by I, it only exists on the leading diagonals. So this ends up being minus 1 minus lambda into A, 3, 8 minus lambda. You find the determinant of that, you set it equal to 0. So it's this times this minus this times this. You expand it out, and this is the answer there. The Cayley-Hamilton theorem says that a matrix is the solution to its own characteristic equation. So we replace these lambdas here with these a's. You also have to replace this term, or change this term a little bit, to times it by I, because this thing is a 2 by 2 matrix, obviously, so it makes no sense to just take away a number from that. So you have to put in an I here to make all this matrices and make it make sense. But anyway, from here, obviously we're trying to get to an a cubed, so we just go times everything by a. And then we've got an a squared here, which we don't want. But okay, this equation here has a squared in terms of other things, essentially. So we're just going to back substitute this line into this one. To get this, just replacing this a squared with just the rearranged version of that and putting it in. And then you expand out and you collect together and stuff, and you eventually get to here. And yeah, we just need to set 57 plus 3a equal to 1, because that's the coefficient in the thing they've given us. Solve that for a, and then throw that into here to find what b is. And we'll end up with this and this as our two answers. You don't have to do this to start with on this question, but I just replaced z with x plus iy and just went to find the Cartesian equation, because that's what you always do on these questions, even though for part A it's actually not necessary. But anyway, so you just arrange these things for real and imaginary parts, and then you just get rid of the moduluses by using this idea, where we can just say that this modulus is this thing squared plus this thing squared, and get rid of the i's, which is useful. Square everything, we get this, start doing some rearranging. And eventually you go down to here, complete the square, and you eventually get to this thing here. So that's the Cartesian equation of this. So it's center minus 2 minus 4 radius root 20, I guess. Show that minus 4, 8i, and the origin pass through this. So we could just use this now. You could have just thrown these straight into here, as I said. But okay, well, the origin is 0, 0 in terms of x, y coordinates. So put 0, 0 in there, and you end up with 2 squared plus 4 squared, which definitely equals 20. So that's fine. And you can do the same thing for the other two. I couldn't actually roll to do it properly, but it all works out well. So that's fine. Sketch an diagram the locus. So like I said, now that you've got this, it's pretty easy. It's a circle, center minus 2 minus 4, so it's down here somewhere, radius root 20. So it looks a bit like this. It goes through the origin, so you can draw the circle comfortably like this, and just make sure it goes through the origin there, as we already discussed. And yeah, that's about that. On your sketch, shade the region such that this and this is true. Well, this is just a circle radius 4, centered at the origin. 4 is less than root 20, so it's a slightly smaller circle, maybe looking a bit like this. And we want we don't want to be equal to this, so we're not on the black locus anymore. We're either side of it, whether we're on the outside or the inside, I'm not sure. But look at this, we've got z to 6, so the key point is the point 6, and to minus 3i, because remember you have to write this as z minus 3i. So we're going to minus 3i, and essentially what we're saying, what this locus represents, based on this idea, is that the distance to 3i is half the distance to 6. So this distance here to 6 is double that to 3i. That's kind of what this is saying here. Now we want it to be more than double the distance into it. So we're going to want to be inside this black circle. For example, this point here is more than twice as far away from there as it is to there. So we want to be inside the black circle for this thing here. And therefore, if we're satisfying both, we need to be inside both, and therefore in that blue shaded region just there. Question 3, so 20% decrease is 0.8, which is where this 0.8 is going to come from. This is, of course, just going to represent the initial number. And then the 20 times the 0.8 represents 20% decrease, I guess. And then the 20 times n plus 1 is because you add 20 times the new subscribers in week n, but you're calculating n plus 1, so you do 20 times the week n plus 1, because at the end of week n, the channel gains 20 new subscribers. So at the end of week n plus 1, the channel gains n plus 1 times 20 subscribers. And then you just say, therefore, it's this. I guess is I think that's probably enough, but anyway. By induction, prove this thing here. So, okay, well, we just let n equals 1 first. You throw it in there. So I've put n equals 1 into this. You type it into a calculator, or you just calculate it by hand. It equals 25, but that's a known value. That's known to be correct. So we are definitely fine. And that's all good to go. We now assume that it's true for n equals k. So we're going to assume this thing here for n equals k. And now we're going to now have to investigate n equals k plus 1. Now, we can't just obviously put k plus 1 into here, because that's what we're trying to show. What's the other thing that we have? Well, we have this thing up here. U k plus 1 is known to be 0.8 u k plus 20 into k plus 1. And now let's work with this, because we know from the assumption step that UK is this thing here, so we can throw that in by the assumption, and now expand out this 4/5. I've changed this 0.8 to 4/5, by the way, because obviously that makes a lot of sense when you're aiming for something with 4/5 in it. 4/5 times this just raises the power up by 1. Expand the rest of it out, collect all these terms together, and you end up with that. But this is okay, because k can kind of be written, I guess, as k plus 1 minus 1. And that's fantastic, because now this thing matches. In here, we've changed a k for a k plus 1, so that's all good. This 100k could just be written as 100k plus 1. That gives you an extra 100, which you don't want, so you remove it, and then you end up perfectly with minus 400. And so this is definitely true. And then you write the thing that you always write, which is, if it's ever true for n equals k, it's true for n equals k plus 1, it's true for n equals 1, therefore it's true for all integer values of n greater or equal to 1. Something like that will do. You write it down, and it's fine. 6 months, I imagine lots of people messed up here because they didn't read that n is measured in weeks. It's asked you for 6 months. I mean, a year is 52 weeks, so I just halved that to get 26 weeks, and then just threw 26 into there and calculated. Is this? That's quite a long way from that, I think, is what I said. I mean, it's not that far away, but it's yeah, whatever. So Euclidean algorithm then says that you take the bigger number and you take away copies of the smaller number until you arrive at the biggest thing you can that's bigger than 0. Sorry, the smallest thing you can that's bigger than 0. So if you take away another copy of 66, you get to less than 0. If you only took away one copy of 66, you could take away another to get down to 36. So this is what we'll do to start. Then you just repeat the process, but with these two numbers. So 66 minus 36, you can only do that once, otherwise you'll get below 0. And then 36 minus 30, again, only once, you get to 6. Then 30, take away 5 lots of 6 goes to 0. And because 6 is the last non-zero remainder, the highest form factor is therefore 6. Use back substitution to get this. So we start with this line here. And we say that 30 is 66 minus 30, so we'll put that in. We can rearrange this to look a bit like this. It's 2 copies of 36 minus 66. And then we can replace this 36 with this line here, just replacing that 36 with that. So this is 2 copies of 168 minus 5 copies of 66. You can obviously always check that in the calculator to make sure you got it right, but we have that A is 2 and B is minus 5. Explain why there are no institute solutions to this. Well, because the highest form factor of 66 and 168 is 6, the answer to this must be a multiple of 6, and 10 isn't a multiple of 6. So that's basically all you have to say there. Solve the congruence equation this. Now, what you're supposed to do here is notice that this equation gets you down to this one quite easily, because, you know, this is a multiple of 11 and stuff. I didn't notice that, so I just did the question as if we had just been given this as the only question to do. But that's fine. It just gives us time to practice this same kind of thing. The highest form factor of these two is 1. You can prove it by doing Euclidean algorithm really quickly. But once you've done that, I guess, you can then just do some back substitution, starting at this line and then maybe putting in this next one here for the 6's is what I've done here. And you eventually end up with this thing here. And now what I can say here is, if I rearrange that just a little bit, I'll get to here. Yeah, sure. Which means that if I take mod of 28 to both sides here, what I've shown, because this term would obviously go away because it's a multiple of 28, what I've shown is that minus 5 is the multiplicative inverse of 11 in the mod 28 world. So if I times this by minus 5, I'll get V is congruent to minus 40 mod 28. Add a couple of copies of 28. I think this is actually enough for the answer, but if you do add a couple of copies of 28, you get to 16, and that'll be the answer. But finding the multiplicative inverse is generally just the way to do that question, which you can always get by doing the highest common factor thing, which is nice. Question 5 then, a code is made of 4 digits followed by 3 distinct letters. So the 4 digits can be from these 5 numbers here. So that's just a choice of 5 times 5 times 5 times 5 things, because they don't have to be distinct. So that's just 5 to the power 4. And then the letters do have to be distinct. So you have 4 choices for the first, then 3, because there's only 3 left for the second, and then 2. And you times that together, you get this. For more codes, a new rule is that the letters can go anywhere as long as they don't go next to each other. So what you can do here is you can choose the numbers again, which is still just 5 to the power 4. Then just put them all down. And what you have to do now is you can put the letters anywhere you want, as long as they go in one of the gaps between the numbers. So you could put a letter here and here and here, for instance. But you can't put more than one in the same gap. You just must put 5 letters. Sorry, you must put 3 letters in one of these 5 gaps. That's going to be 5, choose 3. And and then of course you're going to have to do the 4 times 3 times 2 thing that you did before, because you can, of course, choose different letters to do that with. So it's just going to be this, and it's this times this, which is the same as what we had before, times 5 choose 3, which is 10. So therefore, it's just an extra 0 on top. And then to find the increase in the number, you do this, take away this, and you get this answer here. You now have a lock that consists of 4 distinct digits that can be read like this. All the digits are odd, so they're between 1, 3, 5, 7, and 9. N is divisible by 9. That means the digit sum has to be a multiple of 9. And now just choose 4 of these numbers in turn. So maybe just ignore the 1, add the rest of them up. Do they make a multiple of 9? No. Take away the 3, add the rest up, because they all have to be different, right? Do they make a multiple of 9? No. Actually, the only one that does is 1359, which means if the digits appear in either ascending or descending order, the only codes that you're allowed here are 1359 or 9531. The last rule to decide which one of these two things it is that n has to be congruent to e, which is the missing digit. In both cases, that's 7. So n has to be congruent to 7 mod AB, where AB isn't a times b, it's just AB as a two-digit number. So in this case, 7 mod 13. Now we just want to test this first one, because if the first one works, then great, it's the answer. If it doesn't work, then the other one must be, and that's the answer. So let's just test this. You can just type this divided by 13 in the calculator and read the remainder. It's this, so therefore it's correct, and that will be the answer to this question. Question number 6 then is our recurrence relation. So we're going to rearrange this maybe to make this. Now this is just the same as a differential equation, isn't it? It's just of the form m squared minus 2m plus 4/3 equals 0. Solve that for m. It ends up being a complex number. Now the only difference here with differential equations is you're allowed to be super lazy and just write the complex numbers like this and not bother with the cos sign thing. And actually in this case, it works really well if you do that. So just write it like this. And then of course the same thing as differential equations again. Write un is maybe kn plus c, and then the next term is obviously just this, the term after that is this. Throw those three things into this equation here. And now we just need to compare, after we've kind of expanded it out, compare things that are n's and things that aren't n's. So over here we have kn's minus 2kn's plus 4/3 kn's must equal 1n. And so we solve for k. And then with the things that don't have an n next, then we have 2k plus c minus 2k minus 2c plus 4/3 c equals nothing. But actually, look, all the k's just cancel. You're just left with c's. And if they make 0, then c must be 0. So it's actually not too bad to solve. And you end up with this as the whole answer. The k is 3, the c is 0. So this term over here just becomes 3n. And that's just what I've got there. Now we use the initial conditions. U0 is 1. So if we put n is 0 in here, we get 1 out. Of course, this just ends up being a plus b, which is nice. And if we put in 4, n is 1, we get 4. So we get this here. So a plus b equals 1. Now here, what I did was I just expanded this out and grouped things up a little bit for complex bits and non-complex bits. So a plus b not complex, and then a of this and b of this, and then you can factorize out this stuff here to get this. And now, again, a plus b is 1, so that makes a lot of sense. So that goes away together. But the complex number over here must be equal to 0 because there's no complex number over here. So therefore, a minus b is 0. And now if you solve these two very simple simultaneous equations, you get a as a half and b as a half, which can go into the answer, and you'll have the whole thing done. Worth noting, I don't actually have a scientific calculator to hand. I would be interested to know whether a scientific calculator could solve this and this if you just typed it straight in, using this as a coefficient. I don't know whether it can. I'd be interested to know. Anyway, the set G is the real numbers without the number minus 3/2. With this operation, to find the identity, so the identity would be x times, or composed with the identity, we'll just call the identity e, equals 3 lots of e plus e, sorry, 3 lots of x plus e plus 1 plus 2e xe. But also the identity forces x, when combined with it, to be x. So therefore we'd have x equals this thing with the e's as the y. So I didn't say that very well, I don't think. But x composed with e not only gets you x, because that's the whole point of the identity element e, but it also gets you, of course, this with e as your y, or y as the e, I guess. So you end up with this. This doesn't look very hopeful, but when you actually rearrange this for e by just grouping up together and dividing, you end up being able to cancel these things out. So e just becomes minus 1, which is nice. So therefore e is minus 1, and we're done. The inverse, or the inverse is the element that sends x to e. So x times, let's just call the inverse z. X composed with z would just give you e. But we know E is -1 because we just calculated that. And we know X composed with Z is just this with some Z's in it. So we can just put that in. And again, we'll just rearrange this for Z in the same way. And we end up with this here, which I think is the answer that it wanted. And explain why -3/2 must be excluded. Well, if you put X as -3/2 in here, you'll end up with something being divided by 0, and you won't have an inverse element for that element there. So because -3/2 doesn't have an inverse, it must be excluded from the group, because in a group, every element must have an inverse. Question number 8 then is the reduction formula question. So looking at what we're trying to get to, you're going to have to do integration by parts, because that's almost always how these work. Looking at this, there's a divide by 4 thing here. So that's a pretty big hint that we should be integrating this one to get a divide by 4 and then differentiating this one. So if you're not comfortable with how I do integration by parts, let me not explain it to you because I can't be bothered. Basically, it's just you integrate whichever one you want to, and you integrate it 2 times, once here and once there. You leave the other bit alone the first time, and then you differentiate it the second time, which gets you this, and then you slam a minus integral sign in between. You also need to evaluate this one between 2 and 0, but it's just a super quick way of doing it without having to write the dx, dv, du, d, whatever it is that regular people write. It's just much quicker. Anyway, you start evaluating this. This is not something we can integrate, but however, once you take out the quarter n, you notice that, of course, it's just in -1 based on the definition, which is really nice. So that's just in -1. This we just need to figure out the answer to. I guess this just goes away. We want an n-2 here, so I think we just need to times it by -2 another twice to sort of hash that in there and make it work. And -2 squared is 4, so that cancels with that, and you just end up with a minus, which is what they wanted. So a is just -2, and we're done there. Hence determine this value then. Well, we can see that we're using n to be 2 here. So let's just use this formula with n equals 2. We just get this, and we end up with I1 over there. But then we can use the formula for 1 as well, because it's n is bigger or equal to 1. So we can use the formula for I1 as well, once we've simplified that a little bit. I1 is just when you put a 0 in here, sorry, when you put a 1 in there, of course, and then you end up with an I0 all the way over there. Now, you can't use the formula for I0. I've just done a little bit of basic maths there. You can't use the formula for I0, but you can just evaluate I0, because when you put in 0 here, this term just goes away, and you end up just with the integral of e to the 4x, which is obviously super easy to evaluate. It's just a quarter e to the 4x. So that's where I'll take it from here, and then you put the numbers in, and eventually you type this into a calculator. Maybe just ignore this bit so that you can get all the numbery bits done, and you get this bit, and then you just have that bit on its own over there as well. And that's question 8 done as well. We've got another complex number question to do here. Quite a cool question. We have the sort of minor arc of a circle. If we imagine a circle coming around here, we have Z1 is this, Z2 is this, and Z3 kind of in here is that there. Work out the center. Now, there's a couple of ways to do this. You could consider distances to places to work out the center. The easier way is just draw a line between Z3 and Z1 and use a circle theorem that's not used a whole amount, which is the perpendicular bisector of 2 points on the edge of a circle passes through the center of said circle. So if we work out the perpendicular, if we work out the midpoint between Z2 and Z3, that must have the same x coordinate, I guess, as the circle, because what's useful about Z2 and Z3 is they're both at the same height. So therefore, this line is heading straight down. So whatever this x coordinate is, that's the same as this x coordinate, which is what we wanted to show, which we know is -1, which means, to sum all that up, this x coordinate, which is essentially a, plus this 1 divided by 2 is equal to the -1. The average of those two x coordinates must be the -1 that we know the center to be at, because this is a vertical line, because these two are at the same height, so make a horizontal line. So anyway, from that we get it as -3, I guess. Quite a cool question there. Again, you could do it with Pythagoras and distances, but it's easier to do it that way. Hence, determine a complex equation for the locus. So yeah, the equation for an arc like this, of course, is this whole thing. Argument of z minus z1 over z minus z2 equals theta. Now, z1 and z2 need to be the two edges of it. So we are going to use this z1 as this z2 here. Now, this arc always goes anti-clockwise, which is why the z1 needs to be on top. So it can go anti-clockwise to the z2 down here. So we can just put those values in there like this. But then we know that the 0.1 plus 4i is on this loci here. So we can put that point in there, like this. Just putting the point that we know z3 in there. Now simplify it and simplify it some more. And what is the argument of minus a half plus a half I? Well, it's over here somewhere, right? Minus a half plus a half I. And it's at 45 degrees, or pi over 4, because it's obviously equal. So it's pi over 2 plus pi over 4 is 3 pi over 4. And so that's the argument. So now we can just say the whole loci is just this. Just putting theta in there, and we just get this as our answer, I think. Quite a nice question. And finally, we have the surface area question. So let's do a bunch of things here. We first look in the formula book for the surface area generated when going around x. It's this. And now, okay, we've got a lot to do here. Let's find dy by dx. You raise that to the power half, and then do some chain rule. So the half comes down. You take away 1 from there, and then you times by the derivative of this thing here, which is 2x over 9. You can do a bunch of things. I mean, you need to square that, right? So we square both of it, I guess. That's me squaring it. I think I started tidying this up a little bit, combining this together, and then I can flip it over. I can also cancel out a 9, which is helpful. I can cancel out these 4s from earlier. I can put this x squared in there, and then I can add 1 to both sides. And I think that's what I then threw into here. We also need, of course, dx. Did I work that out earlier? No, oh, sorry, we don't need dx, of course, because we're just going to put this y in here as well, and everything will be in terms of x, of course. Cool, so we're going to put all that in there, in between 4 and minus 4, because that's what it says here, so between 4 and minus 4. And then we can start doing some more stuff. These halves can just go out to the outside, because they're both to the power half, so that's fine. So now we can just multiply these two things together, except I'm actually going to combine them first. I'm not going to multiply them, I'm just going to combine them. I think I factorized out a 9th from this one here, and then I can pull it out and halve it, or half power it to make a 3rd, and then I can multiply these things, or I can just notice these two things cancel now, or they will once I put them together with this 9 here. Now these two things cancel. You can pull another 1/9 out to make another 1/3 to make a 9th out here in total, and then I think the whole thing just works. That's not very good cancelling, but this thing's supposed to cancel with this thing. Then I think the whole thing just works exactly as you wanted, where p is 1/9. Sorry, is 2/9 once you pull that out there and put it at the front. Where does this plus q pi come from? Well, actually, it's asked you for the total surface area. So that's not just the surface when you've revolved this around, but it's also the 2 circles you get on either end. Now, if x is 4 over here, that means the height, just put x as 4 and you get the height is 5 over 3. So therefore, you can just say that the area of this circle is pi times 5 over 3 squared. And there's 2 of those, so we have to add 2 of those in there, which eventually gives you this, and that'll be the whole thing there. Then it says use the substitution. Now, obviously, the actual substitution to use here, I think, is I sec squared, which would allow you to then solve this question properly, but it's asked us to use this. Actually, it said we could use something else, but whatever. I use this. We can say that this is symmetrical, so double this and just use a 0 there. It just makes the substitution at the end easier, is the first thing I did. And then dx is this, sine just differentiates straight to, sorry, sine differentiates straight to cos, that's easy. Square both of them, or square this, and you just get this, again, very straightforward. Now, this here is me just trying to change this limit. Now, you can just times by root 10 divided by 9, I guess. And R shine is something you can do in a calculator, so you can just find that is roughly this. R shine of 0 is just 0, so that's fine. That can just go away. And we eventually, after all of that, just end up with this here. So that's me replacing all of that. You can factorize out the 81 and root it to give you a 9 into this. This, based on this formula here, is just cosh squared, which roots to cosh. So you end up with cosh squared based on this other one. You pull all the numbers out, and then the integral of cosh squared is the last thing you have to do in this paper, basically. But you can use this result here to help you with that, because you already know sine squared is 1, what is it, cosh squared minus 1, I guess. That makes 2 cosh squared minus 1 is cosh 2x. Rearrange for cosh squared, and you get this, throw that in there, and then all of this is super easy to integrate. And then again, your calculator can just work out sine of certain values, so you're good to just type it all in, and we're good to go, and we'll end up with the answer of about 81.